This is a brief extension of the discussion on the Riemann integral, and in this case extended it to the differential of the CDF as a function f of x. And this is just to make clear the notation that we will sometimes use. So if we consider a small difference in our function f of x as being f evaluated at x plus a small change in x, and subtract from that simply f of x, then our differential of f of x is the limit as delta x goes to 0 of that difference, which is written here as the CDF at x plus dx minus the CDF at x. Now if we take our Riemann integral and essentially use the same definition, we're going to chop up the range from a to b, in this case a to b, and just chop it up into a really infinitesimally small partition. And we are going to look at the pick a particular xi, and then we look at the differential with related to xi times the function value at xi, and then sum that across all of the i's. Essentially that's what we're doing. Notice that what we do is we find an xi for each I of this set of values in our partition of the line segment A to B. We evaluate the function at xi, and then we evaluate the differential at xi, which is to evaluate this component right here. And we take the sum of that across this interval from a to b, and that's our integral. So really it's the same concept and definition as the Riemann integral with respect to dx, where we simply took, instead of df, we took dx. And how can we convert from one to the other? Well, notice that our differential of x is, as written above, is our CDF at x plus dx minus the CDF at x. Simply multiply by dx, divide by dx. And this quantity here, which is that differential of f of x divided by dx, is typically what we have as our density. And so really dx is equal to the density at x, df of x is equal to the density of x times dx. So we can substitute that in, and we have our integral from a to b gx df of x, which is the same thing as the integral from a to b gx little f of x times dx. So there's two different ways that we can express the integral of interest. This is the more classic way to do so, but we can write it this way as well, and we will do this quite often. So either expression is fine for expressing our integrals.